Hello, my name is McQuarrie. I write a set of column articles in PCB007. It's an internet publication for the printed circuit board industry. My column is called Solving Damn Problems. In this article, Are We Nothing More Than a Pair of Socks at Walmart? I talk about using a discrete event model to look at the issues of dealing with finite plant capacity. And we do that by taking the discrete event model that's shown here in Figure 1 and then doing a design of experiment and then fitting the data using a neural net that you can do in JUMP. And this is very exciting stuff. So we're going to get into the details of how we did that DOE so you understand it better. But before we do that, we really should clean up this model because it's really kind of messy, and we can make this look a whole lot better. Now, a discrete event model has blocks. These green blocks are for passing items, which is the things that you care about. That's the product, and you want to keep track of that. And you can keep track of every single item in a discrete event simulation using the ExtendSim software, which is what I'm using. These yellow blocks are for calculations. So it's looking really messy. So I'm going to clean this up. What I'm going to do is I'm going to select these blocks right here. And I'm going to make another block that combines all of these blocks. I'm going to call this the accounting block. And it looks pretty clean. This is an equation block, and this computes the profit. And here the profit is equal to the panel price times panels in lot times the number of lots minus the expenses. So I'm going to put that in the accounting block. In fact, I'm going to name that the accounting block. I'm naming it here so we can actually see the name outside of the block, so it isn't just a big gray box. So I'm going to take this, cut that, and what we see here is this thing for lots isn't getting connected. And that's really coming in from this second input connector. So what I'm going to do is I'm going to move this over here and clean this up. And then connect it like this, like so. And it's not the tidiest, but it gets the job done in terms of looking at the outside. So what I'm going to do next is I'm going to clean up the rest of these blocks. And here we see the improved model. We have an accounting block that I changed and moved around. And that's one of the advantages of having these hierarchical blocks is you can move stuff out of the way so you can focus on the big stuff. And here's a production block that cleaned everything up. We have the number of conveyor items and the number of items waiting, and when you add that up, you get the total WIP. And then coming out is the scrap fraction, which tells it whether it's a good board or a bad board on this routing block that I have highlighted. Let's run this and see what it looks like. When we run it, we can see that the panels are piling up on the conveyor and bags of money are getting collected up there, but we're not getting any really good information at us. It's not obvious where we can put some inputs and run different cases and follow our intuition and experiment in sort of an ad hoc way before we do a design of experiment. So this isn't really a desirable setup yet. So I'm going to stop this. I'm going to move this model out of the way. What I'm going to show you next is one where it's laid out a lot nicer and a lot cleaner. We have this very long conveyor belt. In fact, we have two conveyor belts because then we can look at the reliability effect when one conveyor belt is breaking down more than the other, and this can be specified in this reliability block. The scheduling block explains how we can start lots per day, and we can change that number, which we're going to do in the design of experiment. This is a quality control block where we can change the scrap fraction, which we're going to change in the design of experiment. All of this is really good stuff. The efficiency of the line and what's going on. And this is telling us the downtimes, and this accounting block or accounts payable block is where we do the bags of money to keep the doors going. The sales block is where we can change the price per panel, and then we have the accounting block. Let's run this. We got 500 days time before failure in line 1. Time before failure in line 2 is, let's change that also to 500 days. What that's going to mean is, since this is a 72-day simulation, it's going to be very unlikely that we're going to have a breakdown in the line. Let's run this and let's see what happens. And when we run this, we see the paperwork for the starts, or the travelers, and the travelers then tell production how much to release. Boards get released and they move down the conveyor belt and then onto the second conveyor belt, and we see nothing is accumulating at the first queue except for at the start of the day. Nothing is accumulating in the second queue. We have a very stable production situation. We have some numbers here to tell us what's getting scrapped. And this is really identical the way we have this set up to the model that was described in the paper. And so we can use this to conduct an experiment. Let's finish off this simulation. I'm just going to hit and let it trigger all the way through. And the simulation is done, and we can see in this particular instance we had a nice profitable situation. This shows that we're very close to Little's law in terms of our amount of WIP, which means we have a very stable production line, and that our throughput is much higher than our practical worst case throughput, which will be, all of this will be discussed in a future article. And we had absolutely no downtime, so as we see in the maintenance block. So the next step is to do a design of experiment.